Good day, everyone. Welcome to Gaia STEM lecture series of Taiwan Top Science Student Project. I'm today's host, Juling Shih from National Central University, Taiwan. I'd like to introduce our speaker today, Professor Hsin-I Chang from the Department of Hydrology and Atmospheric Sciences, University of Arizona. Professor Chang is a climate scientist specializing in regional climate modeling in the arid and semi-arid region. Her main research interests including understanding the variability of extremes at weather and climate timescales, and the influence of climate change on North American monsoon variability, and the representation of land atmospheric interactions and convective processes through modeling and field experiments. She is one of the core contributors to the North American Coordinated Regional Downscaling Experiment. Professor Zhang's climate research outcome also led to the translation of complex scientific findings for decision-making for the public and private sectors. Having that said, we shall welcome Professor Zhang right now to give her talk on the topic of historic and future extreme climate assessments over arid and semi-arid regions and the application for risk management. Let's welcome Professor Zhang. 张老师
Okay,
please.
谢谢. Thank you, Professor Shih, for the introduction. Just give me 1 second to put the slide in the presentation mode. You can see this okay? Great. Okay, so hi everybody. I'm Hsin-I Chang. I am a faculty at University of Arizona Hydrology and Atmospheric Science Department, also the director of Center for Applied Hydroclimate Sciences. So the topic today is a combination of my recent research publications as well as some very new ongoing research activities. Okay, great. So I'd like to introduce a little bit of what is the Center of Applied Hydroclimate Sciences is. So this is a relatively young research center within the University of Arizona. We started about 4 years ago, and the objective and the vision for this research center is really to apply the physics-based and science-based information to support decision-making with a goal to increase environmental resilience. And the mission is really to bridge this kind of research community within the university and the national lab and connecting the private and public sector to really deliver this kind of tailored information for generation and applications. So the map you're seeing on the left is the top left corner is the map of the Western United States, and then the Colorado River Basin is highlighted in the different blue area. There's upper basin and lower basin. Why we highlight this is because the Colorado River Basin provides actually the majority of the water resource over the Western United States. So imagine how many millions of people would rely on the Colorado River Basin for the water resources. So we started from looking into this the basin study and then expanded to the complex terrain and arid and semi-arid region and also the American monsoon. So just a little bit of the key activities related to the CAS, that's how we call it. So their main three components are research, service, and outreach. So today I will touch base on all three of this. So first of all, the research, of course, what is the weather and climate related research in hydrology and atmospheric sciences, providing the physics-based information through modeling and machine learning approach, and then developing the tools and that lead to the service part, which is providing tailored information for the stakeholders as well as the collaborators to use. Then the outreach component is because we're in the university, so a very significant portion of our activity is related to student training and also training data users as well as support, information support. So this is a introduction of my research in the temporal time scale. So if you see, if you can, so you can see the diagram on display here is provided by National Academy report in 2016, highlighting the different forecasting time scale that is on the x-axis related to what kind of information needed. For example, within a few minutes to days, this is where we're used to the weather forecasting time scale that you see on TV, like what's happening in the next 2 to 5 days, kind of the forecast. So that's called a weather forecast. Then the middle part is where we get into the subseasonal to seasonal part. That's a 2 weeks to 2 months, this kind of projection period, this and forecast period. This is where we're getting into the seasonal variability, and which this is the part that not many people are focusing on, but I will show some of the examples from my research. Then last but not least is the extended time step where we have the decadal kind of climate scale kind of projection. So that is that goes into the climate projection project I'm working on right now. So the main tool I'm using is a physics-based region climate modeling model, and the focus area is in the semi-arid and semi-arid region. So it's not just for the Southwest or the Western United States. It's actually for North America, for South America, for the some Middle East area. So you will see a little bit of example today as well. And then,
Yes.
so this is a highlight of my research activities, from short-term weather forecast to understanding the dynamics of the North American monsoon, from initiation to the result of extreme and the longer term variability, how we design the climate assessment with specific stakeholders, from different projection scenarios to different model approaches. And then the lower panels are getting into, for example, the subseasonal forecasting design operationally for visualization, and how do we really produce the usable information for different data users. And lastly, but not least, what is the probability of projection for a specific variable of interest? So this is a simplified diagram of how the physics-based modeling design that my group has been working on for a long time. So this is a process of dynamical downscaling from using the global climate model from the left-hand side that is really much coarser resolution at the meso-alpha scale, that and it is provided that cover the entire globe. And then through dynamical downscaling and with the application of regional climate model, that in the middle, we were able to really downscale the climate simulations as well as the weather forecasting type of simulation to the scale that is about meso beta domain. And then because the United States, as an example here, is very large, so meso beta domain sometimes for some of the regions is sufficient, but for complex terrain like the Southwest or even like Taiwan is a very small area, the meso gamma domain is needed. That is what is happening on the further right-hand side when we have the resolution that goes down to the sub 5-kilometer resolution. So some introduction of what I did in the climate projections. So Dr. Shih has introduced my work for the NA-Quad Access Coordinated Regional Climate Downscaling Experiment in North America. So this is a community effort supported by and volunteered by scientists who really donate their time and computing resources to create this kind of continuous climate projection downscaling work. And for North America, this is the domain you're seeing on the left-hand side. And I've completed the CMF5 downscaling with my colleagues in Ankara and other universities. And this is designed with a combination of different global climate model with two different regional climate model and various resolution at the highest greenhouse gas emission scenario. So the table here, you can find this in the link here, but whatever that is highlighted in red are the core simulations that we produced, and then these data set is already available for use, and also a very small group of climate scientists within the United States, and we've identified a new SSP scenarios, and then this is in agreement with the international Cortex community with the kind of targeted SSP that is in response to the global climate agreement, and then also the downscaling modeling design as well as bias correction and all the different tuning and so first of all, when we are looking at the climate projections, and so the two maps here I'm showing is a zoomed in version of the NA Core X map that we're seeing right here. So it's like the Southwest United States as well as Mexico. So for this, the first look we're looking at is the changes like people when they think about climate projection or the climate changes, the signal of how the precipitation is changing, that this is what I'm showing right now, is we first look at the annual precipitation change on the left, and also on the right is the annual maxima change. So on the right here. So this kind of change, like what you're seeing is, okay, so the annual precipitation, it doesn't look like there's changing a lot, right? So the range is about plus to minus 10% for this kind of for future projection precipitation change. Then when you look at the annual maxima, you started to see a little bit more of the spatial difference in terms of it really depends on where you look at. For the annual maxima change, you see some of the several very large area in the Mexico area is actually having a positive change in precipitation change from maybe 10% to the 30% range. But when we go into the Southern California, Southern Arizona, you start to see pockets of decreasing in precipitation. So what does it mean? And then and also, when you dive into seasonal variability, it becomes even more confusing, if I can say it this way. So on the left-hand side, this four panels are again is the annual mean precipitation change, and on the right-hand side, these four panels are the annual maxima change in the seasonal way. So let's look at the mean change first. Like looking at the mean change, it looks like summertime has the most significant reduction in the mean annual precipitation as compared to the three different seasons. But when you look at the annual maximum on the right-hand side, there's four panels. You started to see that actually, if we're looking at the higher precipitation thresholds, that's where we see the most significant change. You can see the color gets darkened, like darker brown, darker green. That means it is much wetter or much drier, depends on the positive and negative signs. So you can see that the mean precipitation, the range is sort of in the middle, so 10, 20% plus and minus, but then for the extreme side, it actually goes to the further end of either side of the projection. So then great, we see that spatial variability, but how do we use it? And how do stakeholders use it? Just imagine if you're someone who need to plan for your water usage for the next year, for the next season, or in the next 10 years? What's the infrastructure that you need to design in response to this kind of potential water shortage, as well as like extended drought or heat? What do you do? So, and then in general, we have to provide a range of data climate assessment from multiple climate projection sources. So if you recall the NA-Cortex slide that I showed with a table of various different scenarios, the combination, different resolutions, and this is what we did with our collaboration with the America's Bureau of Reclamation. So if you don't know what is this institution, this organization is, though this is a government institution that really in responsible of planning for the national water resources, let's put it this way. And then they really wanted us to provide this kind of climate assessment for the Colorado River basins. So the map here showing is for the lower Santa Cruz River. So this is like closer to the US-Mexico border, and where the Colorado River goes down toward the across the border and comes back. So there's transboundary aquifer that they need to plan, and then because the water resources is shared between two countries, and you have signed a treaty decades ago, so a very complex region here because there are political concerns in addition to the water resource concerns. So what we did is every single dot you see here is one of the climate projection data set. So we have at least 8 to 10 different climate projections that we had to evaluate. And then what we provided was projections of temperature and precipitation changes in the 2030s on the left and 2060s on the right. So the y-axis is the changes in temperature, and the x-axis is the changes in precipitation. So the zero change in precipitation is here, and the zero change in temperature is way down here. So basically, it's not surprising that in the future temperature projection for the near future and far future, we're overall, all the models are projecting warmer future. But how much warmer, it really depends on which model you look at, right? So there is a physics-based models that I produced with my collaborator. There's also statistically based projection from LOCA. So that is another source of climate projection. And also we have to identify what is the best case scenario versus the worst case scenario. So that's what you see on the solid triangle and solid square. So this gives you a range of projection that we're providing to stakeholders, and they need to be able to expect and evaluate and plan their future management operations. So it just happens the data set I created that has the most reasonable representation in historic climate, it happens to be the worst case scenario case. So it means like it projected the warmest for the near future and far future, also as the driest. You can see that is like further to the left in terms of precipitation projection. So these are based on the CMIP-5 Cortex simulations. So we're still working on the CMIP-6. So this kind of assessment will be produced when the CMIP-6 Cortex is complete. So coming back to the projections, and then that you recall, I showed the mean changes, the annual maxima changes. Now this is something new. So the map looks very similar, like the format is the same, but this is done with the probability of extremes. So what we have done is we calculated the probability of extremes for events that is once every 10 years, that's on the left, and once every 100 years on the right. So just imagine if you have an event that usually happens once every 10 years. Usually that is less extreme than an event that only happens once every 100 years. So what we're seeing here is for this kind of 10-year return period event, the probability of extreme happening is the signal is not as strong when we look at the 100-year event on the right-hand side. You're seeing a lot of, there's some area actually has 100% increase in this kind of probability of extremes happening by the end of 21st century. So this work we're in preparation to be submitted to the journal this summer. And you're seeing this for the first time and trying to we're trying to provide some insight in terms of how and why and where this kind of a projection is happening. And then, so this is one of the slides that is part of the manuscript as well, is really to look into the different locations of those extreme signal. So this is the spatial map, right? And then if for this, it's a bit difficult to understand, but I'll walk you through it. So on the y-axis, I have 12 different locations, and you see they're sort of mixed match, like jumbled from 1, 9, 10, and 2, 3, 7. It is because these are grouped spatially. So on the x-axis is the different return period years from very not extreme, like 1.5 to 2-year return period, to the very extreme, that is a 100-year return period. So to help you understand this, I grouped the two groups of stations that has the most consistent signal. So that is on the top here and on the bottom here. So these stations are telling us, okay, so so these stations are geographically similar to, like, located to each other. So for this top group is in the north western side of Mexico, and then so they are very consistently having a increase in the short-term return period, so it's lesser extreme cases, and then for the more extreme cases, actually it is a decrease for those location based. And then for the lower box here is, although these locations are grouped together, and then we're seeing some consistent decrease in those extremes probability in some of the locations, but you do see some are increasing, so it becomes a opposite signal. Why is that? Is it because these, although they are geographically located in the similar vicinity, there's elevation issues, there's also land use and cover issues, also some station is on the lee side of the mountain. So like and compared to the others, and how much precipitation generally it receives climatologically, they are all needed to be considered. So it's not a very easy way and simple way to describe those information. So, so those are the more on the probability of climate projections. And then I want to bring your attention to what I mentioned earlier in the presentation about subseasonal to seasonal timescale forecast. So this is a project that we recently are completed with the King Abdullah University of Science and Technology. So this is in the Arabian Peninsula, where it has the similar climate. So the kingdom is in the arid climate. It also has complex terrain. So a lot of characteristics are similar to where I am right now. So we have been working with them for several years, trying to help them understand these kind of to improve their operational weather forecast, as well as like advancing the forecast capability to 2 weeks to 2 months kind of projection forecast lead time. And with the mission that we're developing a operational forecast, because in this region, there's very limited operational forecasting information you get like daily, and also a lot of times it's after the fact. So the picture here you're seeing is actually one of the largest convective events that occurred within like 36 hours, and then flash flooding come and gone within hours, and then you're left with a lot of debris of cars. So for this kind of study, we have to have a very careful design in terms of the modeling design, trying to understand the signal. So this is subseasonal to seasonal forecast using convective permitting model reforecast simulation. So if for those who doesn't really know what those regional climate modeling needs is, it needs a very four things for lateral and boundary conditions from global GCMs. If you remember the diagram I have from the global model, regional model, and from across different spatial resolutions. So the boundary conditions, like we had to test using ECMWF, and these are the subseasonal reforecast. These are the real analysis. Reanalysis is done with the ERA interim reanalysis, and then we also have to test the configuration and calibrate the model that is suitable for the study region. So we had to do this like kind of standalone verification of this kind of modeling design to create this downscale reanalysis before we can get into this yellow part, portion of the S2S simulation. So for this kind of downscaling, we have to use ensemble-based simulations because that that is one of the critical input that we need because ensemble-based S2S creates a range of forecast boundary as well as the initial condition for us to do the downscaling. We have to test it for the top convective events, which was published earlier. And then so these are the top 20 extreme events near Jeddah area. If you don't know Jeddah, you may know Mecca. So that's right next to Mecca on the coastal region of the Red Sea. And then these and also what I'm going to show you is a result that we just published recently in 2025. And then this is with the 20-year downscaled climatology of those subseasonal to seasonal forecasts. So one of the key thing of this kind of modeling design is we actually have to test forecast capability at different initialization time. So you see that different initialization time from 1 week to 3 weeks. And for the 20-year reforecast downscaling, we have to do it like every 30-day simulation initializing weekly. So it's not an easy task, and we burn millions of core hours, but we were lucky to have one, I think one of the top 10 supercomputers in the world at that time we can play with. So we were able to really develop this kind of downscale climatology. So some very quick results. On the left-hand side is the raw data. Then the raw data from the ECMWF on the top panel from different initialization and the actual regional climate model downscale product on the bottom. And then on the right, this is the difference of what you're seeing on the left. So in short, this kind of downscaling exercise actually we're able to create the forecast S2S type forecast and reduce the bias by 30 to 40%. So we to us, this is a very significant improvement as compared to what they've been relying on using the ECMWF GCM. So we were able to provide this and then design operational forecast website as well as the verification matrix for them to display operationally. So at the summary of this paper, and the entire project with DeKalb University is really to demonstrate the value added using S2S. So the list of relevant publications are here. There are a lot more. Also, we were able to identify the convections over that domain or over the Kingdom of Saudi Arabia, actually how they were driven, like tropical driven versus extratropical driven kind of synoptic conditions. And also this has led to the forecast and evaluation platform in collaboration with Saudi's National Center for Meteorology. And then and this kind of exercise is currently being implemented into like Southwest US as well as the pending Chile project. So the time series on the right is all you need to know is the red is the ECMWF, so the GCM, and the blues are the convective permitting regional climate model product we have. And then you see the blue lines is generally higher than the red line. So the y-axis is showing this the forecast skill. So we generally have a much better forecast skill compared to the ECMWF GCMs from different forecast lead time. So this 1 week lead time and 2 week lead time, that means initializing the forecast 2 weeks before the event, 3 weeks before the event, and 4 weeks before the event. So we're generally performing better. So so the next is tracking those convective extremes. We started this project because we for the region like this, not like the United States, we're very data rich. We can get all the very good coverage of radar measurements as well as satellite product and gauge measurements for the United States and probably for Taiwan as well. But for a region like this, when you may only have 3 to 5 radars for the entire region, so the coverage is limited, and then all the gauge measurements were concentrated in a very well populated area, not like well distributed throughout the kingdom. So how do we do this kind of tracking with to track MCSs and for which usually lead to extreme convections? So we have to do it again, like trying to investigate how we can use the regional climate model as the input instead of the observational based product for input. So what we did, I'm showing here is a brand new result that just came out yesterday. So on the left-hand side here is the case of, so the top 2 convective case in November. So this is November 2009. So this is where JITA is, and this is a cloud, MCS cloud, as well as the MCS cloud track, the core that is in the red. On the bottom is independent source of precipitation from a gridded observation that you see that we were able to track the MCS cloud and matching where the localized convection is at. So this is the wintertime convective precipitation, which usually lead to very significant flooding as well as economic loss. Then something new on the right-hand side is this is the April case, which is the end of the cool season or end of the wet season for them to consider. And for this kind of March, April months, we usually have wider spread precipitation, less concentrated comparing to the November case. And you can see there's a much more widespread of rainfall. And then we were still able to track those convective cores relatively well. So this is actually showing the most largest MCS cloud of this particular event. This will be summarized for our paper that is in preparation that I hopefully to submit this summer. And then we are already submitted another MCS cloud tracking paper that focus on this Great Plains region in the United States. So lastly, this is something that we did for the 20-year regional climate model climatology. So on the left-hand side is all the cloud track density for the month of November for the within 20 years, and then what is the corresponding GPM precipitation in November. So they're quite compatible in terms of the cloud track versus the precipitation. So one thing I want to introduce a bit before I end this presentation is how do we apply those physics-based climate information for private sector and other non-research needs. So this is related to my research center activity. For this one, we have been privileged to work with utility company as well as mining industry to really create this kind of climate assessment report because they're required not only by the local government but also by international financial community. Like some are on the stock market in different countries, so there are requirements of a financial disclosure related to climate change. So we were able to work with them and provide some information for them. So we have to again provide a range of projections for different projection period, like between 2040s to 2060s. And here I'm just showing you how random, how variable those projections could be in terms of precipitation, and then what kind of information we ended up giving them. So on this figure, it's specific for extreme heat assessment. So out of this 400 ensemble projections that we created based on the physics base and the statistical analysis and projection, we were able to assess and summarize extreme heat trend from frequency, duration, intensity, and seasonal length of extreme heat. So you can see the historic is in blue and in black, near future in darker blue, far future in lighter blue, and then the frequency of the extreme heat days was historically 5.3. It increased by 14.9 for near future and then increased further for the far future. So you get the point. And then the whiskers are the range of those ensembles, like how those model agrees with each other. And then we also did this for the precipitation related assessment, again for historic near future and far future, and looking at the seasonal rainfall with different values, and then dry spell and different threshold of rain. So you can see that some of the variable like this higher threshold of extreme rain is actually have wider spread. That means the model is not agreeing with each other, but this is something they actually prefer because they don't want surprises. So they want to be able to prepare for any scenarios that could possibly happening. So they actually don't mind this kind of wider range of projections. So last of the research slide is so on the right hand side, you probably remember what I showed this before. So this is probability of extreme occurrence for the 100-year return period, and I can translate it into the location-based information on here. So the black is observation-based, the red is the model-based projection. So that's for the future. You can see that by the end of 21st century. And then so you're seeing that there's and this is a return period from 2 years to 200 years and different thresholds. So for this, how do you use it? And so translating into the table format, if you look at the format that in purple that you see, okay, observed values of extreme return period that is 10 years, that is 64 millimeter per day. For the 200-year, 163 is considered extreme in observation. And for the future changes, I can show you in percentage, okay, 64% decreased by 9.3% is how much, versus if it's for the 100-year return period, is increased by 233%. But this is still something that they cannot use. My stakeholders, they cannot use this information until I can give you this like further right-hand panel that is a column that is about the multiplier, because the model they use, they have to plug in some value that represents this kind of future change, right? So I cannot give them those negative 0.3, 0.9%. No, they can't do that. But I can give him this kind of multiply, 0.91. Okay, so that means like future is going to have lower precipitation projection, and then at the 10-year return period and 100-year is like 3 times more than it should be. So this is something they can use. So until I can get them to this point, the multiplier, my science-based information is non-usable. So I just want you to keep this in mind. A lot of times is this one last step that creates something that is most critical for them. So, my research has brought me to various interesting places, and with different collaborators, they all share this kind of common interest and feedback when during and after our collaboration is because I work with, like I said, private sector as well as public sector, and so they enjoy the process of working with our research group to develop something together. So, and also because they trust our science, they trust our process, and when we deliver something in collaboration with their team, they trust our data even more, and they become ambassador to promote our product in their own workshops and engagement activities. And then this kind of co-production of knowledge becomes more usable, and it will become more valuable, I would say. So this is a picture that we took 2 years ago when we visited the mine. And then this is actually about 12 meters into the mountains. And then we're standing in one of the few electric trucks in the world, very few. And then if you can see this one in the middle. So it was a very interesting experience. So one of the last things about how we come up with our collaborators for this kind of climate assessment exercise is really to develop I call it an action plan. So you start from, I just show everything because I'm running out of time. So we have to identify the risk, evaluate the risk, and list the impact, consider a different scenario, and make the decision and communicate the decision with external, and then different partners. And then with the core that this kind of process requires traceability and governance. So because without this, you'll get a black box, and then you have questions and then doubts in terms of how much you can use those information and how much you can trust it. So two of the slides I shows the new activities. I've been showing physics-based climate modeling activities and research projects. So there's a new project. We're trying to incorporate machine learning into this kind of hydrologic modeling, and especially for the urban region. So this will start later this summer, supported by NOAA. And then another thing very interesting and very new to me is designing a field campaign with different collaborators with NCAR, NASA, our university, ASU, and Burrito, University of Wyoming. We're trying to understand the monsoon-related convections, and then designing a field campaign that includes not just only modeling component, but also radar, gauge measurement drones, aircraft, as well as different tower stations that centered around a complex terrain region. So these are a schematic diagram of how those measurement instrumentation would be set up, and even balloons that would be launched like every 12 hours. So I'll end with this concluding slide. So I hope you enjoy my physics-based, climate-related, and also extreme weather-related assessment and summary for some of the arid and semi-arid region research. And then our center is posed as the bridge between the research and applications, if I can say that. And then the current ongoing partnership that I'm involved with is, in addition to the assessment workflow developed as well as the climate adaptation training, I am serving as a consultant to utility companies and in collaboration with consulting firm to create this kind of climate assessment report for regional utilities. And then also I'm part of the Consortium for Environmentally Resilient Business. So this is related to the climate impact on the economy. And then last but not least is the tailing center. So this is something related to the mining company because my tailings is one of the critical infrastructure that if the my tailing breaks, the mine waste, if the mine waste was released because of the extreme weather, it will become a very toxic material that endanger the environmental, the surroundings and the cities and the people. So usually the industry is very critical about making sure the infrastructure is safe. So we're starting to work with them to look into the projection of the climate, how we can help them design this kind of mine waste facilities. Um, that's all for today, and I welcome any questions. Thank you.
Yes, thank you for Professor Zhang for giving us a very concise but inspiring talk. Climate change is a complex issue, so we do have several questions. 然后我们今天张老师是可以用中文来做问答的。那我们的聊天室这边呢，其实已经有一些问题了。那不
Okay.
晓得张老师是不是看得到？那 no matter whether you can read it, I'll just read it through.
Okay.
Okay. We sometimes complain that short-term weather forecasts are inaccurate, especially regarding the predicted path and intensity of typhoons. When it comes to longer term climate models, do scientists have any mechanisms or procedures to determine which models are reliable enough to inform decision making with greater confidence? Let's stop here for the first
Okay,
one.
so I'll try to answer in both English and Chinese. So I'll start with English because I see there's some non-Chinese audience here. So a lot of times when we do the climate projection, no matter it's for typhoon or for any kind of monsoon signal or climate projections, we always have to look back into the past first because we with all the climate projections that is like give you a very random signal. How do you pick or choose or people do average of all the ensemble projections to rely on that one line of time series? But our group is trying to understand the pattern of the historic climate before we get into the future. 所以基本上呢，我们在做这些气候变迁的研究的时候，我们必须要有很长的一段时间是在看我们过去的气候的变化。所以说我们的实验除了你看到的，就是以做数据为主的话，我们曾经用过那个 tree ring，就是那个树的年轮的那个 data。然后去看说500年前、1000年前这些树因为降雨强降雨，因为它年轮就会变得比较宽，然后所以我们用那个去因为2000年前可能没有，一定没有水的那个记录嘛，所以我们用年轮来看出，OK，2000年前有很大的降雨，甚至有flooding，所以说我们能够用它来看说那这种。长时间的我们叫 natural variability，就是气候变化，过去气候的变化，然后用它为基准来看说未来的气候变化。因为我们必须要有一个 compatible time period，我不能说我过去的气候我只有给它10年，可是我未来气候我要看它100年，不行，因为它这个 cycle 就不准嘛，就是没有不 match，所以我们必须要有一个很长的 historic climate assessment. I hope that
Okay.
makes sense.
Okay. So let's continue. Additionally, for climate forecasts ranging from several months to seasonal scales and those on the scale of long-term climate change, what differences do these pose for climate scientists?
Okay,
等于是短时
so
间跟长时间的。
因为呢if it's climate projection, decadal climate, so maybe 50 years from now, 100 years from now. So that is climate projection. So for that, because we have to consider the greenhouse emission scenario, the impact of the greenhouse gas scenario. So that becomes that is very different from subseasonal to seasonal. That because uh, greenhouse gas emission will have a lot less impact for the next season compared to 50 years from now. So, 所以基本上呢，就是以气候变迁来讲，如果看的是未来50年、100年的话，你的那些那个什么 CO2 啦，一些 greenhouse gas 的 emission 会比较对那个时候的影响会远远的大于你。它对于下一个季节或是明年的那个比如说夏天的降雨或是台风来不来，台风强度的影响会差别是非常大的。所以说我们必须要用不同的就是你怎么样去看它这个？Again, back to the natural variability，就是那个就像我们有 El Nino 有 La Nina，那每年是不是会不一样？ENSO signal 不一样。那有时候你有很长一段时间都是 El Nino，因为呢海水气温太高了，所以说一直都是很热的状态，所以没有那个 La Nina cycle，就是没有那个 cooling effect。所以这个 cycle 呢是 it happens every few years。它不是下一个季节马上就可以 turn off，所以说我们必须要看的那个就 depends on your target，就是说如果你要看的是气候变迁的几十年后的，那你 definitely need to like be very different from the seasonal variability studies。
就是长期的会比短期的还要来看得多，
对，因为你能看到的时
也
间也
能看到的
比较长，就是
是长的。
你拉长了之后，你就可以看到说，这样说好了，举一个最简单的例子，就是说，我今天这里43度，摄氏43度，可是呢，可能10年后。对我来讲已经是 record，我们这边已经是算是要破纪录了，已经快平纪录，要破纪录。可是可能20年后，43度变成是呃 cooler temperature，你知道吗？所以说我现在的 extreme，我未来可能就不是 extreme 啦，或者是说我今天有一个什么突然下一场大雪，可是你如果以 climate 来看的话，这个大雪可能就是这样子一个小小的一个那个降雨或者是降雪率，然后以那个长时间来看的话，并没有多大的那个impact 在里面。
那我们下一个问题是：Will the Colorado River dry up sometime in the future? If so, what will happen?
Okay, a very good question. So Colorado River, let's put it this way. Colorado River is not just a river, just not just the water. You have to consider snowpack. So, wintertime snow versus summertime rain. So these are the two main sources of water resource in for the Colorado River Basin. So a lot of times is okay, so we would have winters before we have winter snowpack. Then during springtime, snow melt, and then you get the stream flow that gets the water. So it flows into the Colorado River and the sub-river basins. So a lot of times some of the water riverbed here, no, there's no water until there's stream flow or the rain. So I would say it it is dwindling in terms of the the amount of water that is flowing in Colorado, but also the timing is changing. So we could have much earlier stream flow peak because from the snowmelt. Then the summertime is longer time drying, but then we get the extreme convection. So in the future, it is mostly likely instead of regular monsoon rainfall summertime every day, every few days, it could be a longer drought and then very significant convection that delivers some large amount of rainfall. So that's was one of my papers about. So in 说中文，所以说他们问题是说以后的科罗拉多河会不会没有水？可是我觉得不是有没有水，而是你 它的 schedule，它的行程有水的那个时间是会不一样的。像它冬天的降雨冬天的降雪在春天的时候会融化，然后就会变成水流，所以你就会有比较多的水。可是当你气候变迁，你天气变热的时候呢，你那个融雪的时间变早了。那融雪时间变早了之后，你就是可能你要比之前提早很多，还才会去准备去接水，或者是冬天就没有雪了，只有雨了，然后你就变成冬天要去储水。然后再来就是夏天的时候，因为夏天在这个区域呢，它是降雨率呢以美国季风来讲，以前都是没几天就会有一个很频繁的降雨，就是你一定会河里会有水，就有一些河是不是终年有水，就是只有降雨才会有水。然后呢，可是以后可能会变成就是很长的一段时间它是干的。然后可是它突然来一个强降雨，就像我有一些那个Saudi 的 project，它讲的就是突然那个非常非常强的降雨，它可能把半个月一个月的水就一次就给你了。然后你怎么样去接收这些水？因为你水库有没有办法容纳这么多水？所以这个都是一个问题。
好有趣。那我们还有最后一个问题是，Has NOAA, should I say
嗯
NOAA
哼，Yeah,
recent
Noah。
transformation
嗯哼，
had any impact on your ongoing or future research? How is
嗯
your
哼，
lab
嗯哼。
currently responding to these changes?
Okay, so I think NOAA is one. NOAA, NSF, National Science Foundation, several of the climate-related institutions and government-supported institutions are being affected by the current decisions. And then for me, yes, I am definitely directly influenced because of so we have to um, be creative. So that's why my center activity becomes more critical right now because I'm facing the private sector instead of the government funding because all my government funding like the proposal are pending, still under review, it's delayed or uncertain when if the decision will be made, then that's why we as a climate scientist community, we steer our focus in terms of providing climate assessment and climate services to private sectors who are not um, bound to government regulations. They are bound for international regulation, like I mentioned. They have to provide additional financial disclosures to stock markets and then to their investors, to their insurers, and so that is the obligation in addition to the government requirement. And you need to look at industry because industry is international. It's not limited to a country. So that's where we're focusing on is broaden our climate service clients. 所以 in 中文，就是说，现在美国有一些政府的研究机构，就可能有一些经费的缩减啦，然后直接的影响到我们，因为我们做的研究是需要写计划，然后申请经费，然后做跟气候有关系的研究。那现在这一部分呢，很多都是可能它是以暂停的一个status 在那边，它没有直接说就没有不支持这样子的研究，而是他现在是静观其变，这样说好了。所以说我的那个研究中心呢，我们就是呃用更多的时间在跟找那个有关于企业界的对于我们这些气候研究有兴趣有需要的这些公司还有不同的 industry 来合作，因为基本上就像我的 slide 有讲到，像是那个矿业还有那个电力公司，他们都是呃。他们不是只有是在美国境内有，他们的很多的子公司，甚至它有矿在别的国家呀，或者是说它的那个 它的公司不止在美国上市，它在欧洲也上市啊。那所以说，我们必须要以国际化的一个角度来看。所以说，即使说美国的现在的状况不明朗的情况下，可是其他很多国际上面的。这个对于气候这方面的还是非常有他们的需求，那只是说你要怎么样找到这样的需求，然后你要怎么样把你的做完全100%做研究的东西，把它变成是他们可以使用的这个东西，就像我那个 table 一样，就是 multiply，你没有那个 multiply，他们怎么样都用不到。虽然他们很信任你的研究，可是你一定要给他一个他们可以用的东西。然后怎么样去做出这个，就是需要你能够长时间的跟他们去交流，去理解他们想要什么。因为很多时候，像我们做气候研究的时候，然后我跟一个非做研究的人讲了老半天，他听不懂。我们在讲同样的东西，只不过用的词不一样，他就听不懂了。所以你怎么样能够让他们知道说你对于他们的产业是有一些基本的认识的？然后这样子他们反而会
是是，
更有那个兴趣来理解说，那我们可以帮你做什么？所以就这种互惠的这种合作关系是需要长时间的去交流。那这些交流它的基础都还是在于我们做研究这方面是不是有我们的
老师我在等
reputation
你啊。
在，或是有我们的那个就是是不是他们也会去问别人啊，就说哎呀那个谁谁谁他的那个我们想跟他合作，那你们对他们有没有什么看法呀？就是所以说很多时候是你必须要有很好的沟通的技能，然后才会把你的研究能够拓展出去。
谢谢张老师，您回答了我本来想问的问题，就是关于这个合作啊，然后跟这么多方，不包括是government、private sector，还有不同的 university，还有 interdisciplinary people，这样子的一个合作的关系。其实谢谢你刚刚已经先回答了我的问题啊，
太好了，
因为这里面需要很多的沟通的技巧，然后需要很多的努力，然后
是的
把您说的这个比较学术性的东西，把它转换为比较实务性的，make it practical。的这一个部分。
，Yeah，exactly，
那
嗯哼，
那我觉得这个都是对我们听众哈都非常受益的东西。那其实也在我们的科学讲座里面，我们慢慢的也发现，不管我们邀请哪一个领域的科学家，到最后好像大家都是有关系的，因为都是
啊，
一个跨领域的一个合作。对，我
是的，
觉得非常的有趣。那虽然我们时间有超过一点点，但是我还想问最后一个比较 personal 的问题，就是我
嗯哼，
发现心怡老师其实是我们文化大学的
对啊，
大学。那 you speak beautiful English.
哦，thank
What
you，
did you do? Yeah, what did
uh,
you do to make
so I
more
okay, so
prof-
I came here 20 years ago, maybe. But let's put it this way. Should I use Chinese? Okay.
Yeah,
Uh,
either.
okay, so we're talking about how I learn English. 所以说呢，这是给
嗯，
同学们听的。我觉得最重要的，你的耳朵要很好。你的耳朵要很好，你要能够听得出 pronunciation 的不同，就是说那个比如说老师教的呃。就是我们在台湾学的，因为我一直到大学毕业才出国嘛，所以说我的受的英文教育跟你们是一样，可是你们现在可能受的英文教育比我那时候好太多太多，有很多的外师，有很多的机会可以讲。可是对我来讲，最重要的是你要听，你要能够 intonation，就是它整个语调、语气，还有很多时候你那个字，你那个音标你跟着音标发出来的音，跟你实际所谓的一般英语系国家人讲的那个是完全不一样的。there's a vocabulary and then also intonation or accent. So they're all very different. So which one? So you need to make it comfortable. Okay, hold on. 你就把英文当做一个白噪音， 就是说，你必须要
嗯
能够习惯它，就像习惯它，
哼，
就像你变成就是说，你放着一个英文的电影，你也不需要去看字幕，你就能够 recognize what they're saying。然后再来就是 intonation，我觉得很重要的一点就是 how do you how do you speak more like a native? I don't want to. I'm not. I don't sound like a native. I'm trying, but it's not my focus. It's for me is to really um say what you want to say, right? I think one of the critical thing is you like how do you express your thoughts in English without thinking, OK，我也中文是这
对
样讲，然后我翻成英
对
文是这样子，然后脑子再出
对
来。So that's
对，
that's another thing that is very very important. So 你怎么样能够 switch it up？所以这个东西要很长时间的练习，最主要不要怕讲。我常常讲错啊，我现在还是常常讲错啊。然后 who
嗯哼，
cares？反正我能讲，他听得懂就好了。然后还有一个我觉得很重要的是，听笑话很重要。就是听美国的 stand up comedy，我
嗯哼，
就给 I'm giving you a lot of random recommendations。
嗯哼，
美国那些即兴表演的讲笑话的，他那个就是反应要很快，因为你必须要懂得美国的
嗯哼，
文化，你必须要懂得 of course 美国的语
是，
言，还有美国的俚语，这些都是很重要的。呃所以说这些都是现在一定有的 resources，可以去接触。
嗯 Thank you, thank you. 就是 don't be afraid to make mistakes. All we need is communicative English，不是
Yeah,
formal English，
exactly.
对不对？
Exactly. Exactly. So if you can't speak in English without thinking about, am I making a mistake? I think you're 80% there. It doesn't matter if you have a heavy accent. It doesn't matter if you use the wrong grammar. It doesn't matter. It's just like you need to be able to express your thoughts and then communicate, and then that's it. That's all you need to do.
Okay, thank you, Professor Zhang, for the encouragement to our audience.
Of
Thank you
course.
again for a very insightful talk, and thank you for the dynamic interaction. The topic today is one that is very important for human sustainability and risk management. But we haven't got enough time to cover all its aspects. 那尤其是那个关于台湾的部分呢，可能下
嗯
次还要再请张老师给我们做一点提点。就是我们身为
呃
一个台湾人可以做一些什么？Let's keep it for next time
Sure.
啊，
I'll be happy to talk again if I can, and if there's opportunity, of course. And thank you very much for inviting me to this lecture series. I really I've rarely engaged with my Taiwanese communities, and so this is a great opportunity. And I wish I can talk to some of the audience, or engage with them more. But if there's any questions, needs, my email, like feel free to share with the audience again, and I cannot stop if you let me talk. So,
okay, okay, that's good news to us.
okay.
Thank you.
So thank you so
Um,
much.
Thank you. Due to time constraint, we shall end today's session. And before we end today's session, I'd like to announce our next month. We will have Professor Li Hui Cai, Cai Li Hui 老师, Director of the P. Cower Institute for Learning and Memory, Massachusetts Institute of Technology，就是 MIT 的一位老师哈，是蔡立慧老师做认知的。那 Thank you for everybody's participation in our today, event today. Thank you again, Professor Zhang, joining us from 43-degree Arizona area.
Great.
Thank you.
Thank you
See you
guys.
all next month. Next month. Thank you.
Bye.
谢谢，谢
Good
谢，拜
night.
拜。Keep cool.